Now let us consider a situation where our independent variable was through some functional relation producing a dependent variable. But that, as that independent variable increased, it was producing a dependent variable that was not increasing by the same amount, but always getting closer and closer to some fixed value, or that it was decreasing to some fixed value without surpassing it. Now imagine some situations in science where this is true. The half-life of a radioactive material. The activity of the material decreases as time goes on and approaches without ever reaching zero. Another good example is half-value thickness, as X-rays pass through the human body, for example, or cooling curves. There are lots of different situations in which a function may produce an answer that is ever closer to a particular value without ever getting there. Now, mathematics has a notation that can be useful to us here in the physical sciences, and that is the limit notation. Now, I'm going to explain it to you via perhaps the simplest formula that I can think of. Though here's a formula that has no basis in real life, it's just a mathematical formula. So, if you will, imagine this, the number sequence 9 over 10, 99 over 100, 999 over 1000, 9, and on and on and on, forever. Well, if we imagine that each of these in the sequence is denoted by a number n equals 1, and then n equals 2, and n equals 3, and n equals 4, then surely there must be some formula that describes what this fraction is going to do. And what you can see is that as we consider larger and larger n, this fraction is getting closer and closer to 1. That it is 90% of 1 here, and it is 99% of 1 there, and 99.9% of 1 there. It's getting closer to 1. So how can we represent it? Well, first of all, let's find an algebraic expression that describes this. Straight away, 10 to the n would make that number 10, minus 1 would be 9. And so the numerator, it can be represented like this, 10 to the n. And the denominator could just be 10 to the n. That would produce 10 when n was 1, and it would produce 100 when n was 2, etc., etc. Now we can simplify this. A simplification of this formula is 1 minus 1 over 10 to the n. How do we say that this tends to 1 as n tends to infinity? Well, this is when we use the limit notation. And what we say is that the limit as n goes to infinity of 1 minus 1 over 10 to the n is equal to 1, or that 1 minus 1 divided by 10 to the n goes to 1 as n goes to infinity. And so you can see that through this notation we can now describe those functions that produce a value that gets ever closer to some particular level without ever getting there. Now consider this. If x squared, well, what happens to x squared as x squared will go to 16 when x goes to 4? Consider this. Sin x goes to 1 when x goes to pi over 2. And log to the base 10 of x goes to 1 when x goes to 10. And you can see what I'm doing here. I'm using the same notation as before, but in a very different context. No longer have I got a function that is producing a value that is getting ever closer to some set value. I'm actually saying that my function is reaching a certain value as some quantity in it reaches some other quantity. So I can represent this with the same limit notation as used in the previous example. That I know that f of x will go to f of, well, some value when x goes to that value, so long as a is in the range of x. Now imagine we were doing an experiment and there was an independent variable and a dependent variable. Now imagine that we were plotting those in a graph. Y and X. Now imagine that for some reason we have no data collected within a certain area of this graph. So though we have no data here, no data, but that this particular point on the graph that we will call A is of interest to us. Is there anything we've done so far that might help us here? Indeed there is. There is a function of X that was very well defined before it went into this region of no data, and very well defined after. Then you can see visually that we're going to be able to interpolate and take a good guess at what the value of y was when x went to a. And in fact, the value of y, let's call it L, whatever L might be, can be represented in this same notation as well. But what we know is that as x goes to a, y is going to go to L. But because we haven't observed it directly, we would write it with the notation that the limit as x goes to a of the function of x is going to be equal to L. And with this notation, we're able to represent what we mean is that the function itself became indefined in that region where there was no data, if it was experimental procedure, or in a real mathematical situation, it might have just become too close to zero or some such thing like that. But we can use this same notation to represent the area that is undefined. Now imagine if I had a graph where I had a bit of a problem. You see, in the range where x is greater than or equal minus infinity to 0, this part of the graph, imagine that we had a function that was defined like y equals minus x, for example. But in the region of the graph defined as being greater or equal to 0 and smaller or equal to infinity, this part of the graph, the function is more like this: y is equal to x plus 1. Now we have a problem, because as it tends to this point, it looks different whether or not we're travelling towards it this way or we're travelling back towards it that way. So we have to be explicit about the way in which we are approaching this point here. And so what we would say with our limit notation is that the limit as x approaches 0, but from the negative, is that f of x is equal to 0. But in this case, if we come back at it from the other direction and we're travelling down there, what is the value of y when x equals 0? Well, because we're travelling to it from a positive direction, then the function takes the form of 1. And so we use this notation of the limit approaching the value, minus when we are approaching it from the negative, and positive when we're approaching it from the positive, but not necessarily of this point x equals 0, anywhere to the more negative of a particular value, we would annotate with the negative, and anywhere more positive than this value we would annotate with the plus. Now in physics there are some examples of when we might need this. Just imagine that we had a set of angles and there was some part of it that was dependent on tan theta, for example. So this is the function y equals tan x. Y equals tan x has a very interesting discontinuity in the graph at this point here, which is pi over 2, and this point here, which is negative pi over 2. And what we could say in these two places is, let's pick this one here, is that we approach, let's call it g, of x, that this, as the limit is approached from the positive direction, so from pi over 2 positive, then it appears to be right down here at minus infinity. But the limit as x, that should be an x by the way, as x goes to pi over 2 negative, so this is equal to positive infinity. So what you can see is here, using the same notation, we can represent this discontinuity. It depends what it is going to, the direction in which you're approaching it from. Now here is a very interesting test that we can do to any graph, and that is we can have a look at how it looks from both directions and to see if it looks the same. If the limit of f of x as x goes to some value a, whatever that value might be, in a positive direction is equal to the limit of this function of x as x goes towards a from a negative direction, they're equal to each other, then they cannot have a discontinuity. If a is this point here, it satisfies that requirement because it is tending to the same value whether or not you travel towards it or back towards it. Here, this place cannot be a because at this place, travelling forwards towards it does not equal the same as you travel backwards towards it. And so in a mathematically rigorous way, you can identify through this notation whether or not there are discontinuities in your graph. Now, discontinuities do exist in physics, and so you should be aware of them. On a graph which basically looks at the rising temperature of a sample of ice as the energy input goes in as a respective time, there are discontinuities at certain points due to the melting of ice. Now you could define these discontinuities with this similar mathematical notation.